Let's just start with a really simple question. What happens when you pluck a tightly stretched string? Could be a guitar string, could be a massive bridge cable. It vibrates, right? But the rules that govern that vibration, well, they're way more elegant and complex than you might think.
Okay, so to get our heads around this, we're going to start by imagining a totally perfect, idealized cable. It's a classic physics trick, you know? Strip away all the messy stuff to get to the heart of the problem. In this perfect world, our cable is just a flawless, straight line, held under a perfectly constant tension with literally no other forces messing with it. It's a simple, beautiful place to start.
So first things first, we've got to define the rules of this perfect little world of ours. To build a model that we can actually work with, we have to make a few really key assumptions.
And what's kind of wild is just how much we have to simplify. We assume the cable is perfectly straight, we assume its properties, like the tension and its mass, are the same everywhere along its length, and we pretend there's no air resistance and that the vibrations themselves are super, super tiny. By getting rid of all those real-world complications, we can finally see the core physics hiding underneath.
But, of course, the real world is, well, it's not so perfect. And the biggest complication is something we feel every single day, but we tend to forget about in these simple models: gravity.
And this image just lays it all out perfectly. On one side, you have our ideal model, that perfect straight line. But then you look at the real-life example right next to it, and you see what actually happens. Any cable, I don't care how tight you pull it, is going to sag under its own weight. You know, this natural, kind of graceful sag actually has a name. It's called a catenary. And the moment it exists, it breaks one of our biggest rules from before. See, the tension can't possibly be constant if the cable is curved like this. It's actually lowest right in the middle and highest at the ends where it's being held up.
So here's the bottom line. To bridge that gap between our simple little model and this messy reality, our assumptions just aren't going to cut it. We need to find the actual language that governs this motion. We need an equation.
So, how do you even discover a language like that? Well, it turns out the whole process leads us to one of the most famous and honestly most powerful equations in all of physics.
The way they figured this out is just brilliant. Physicists essentially zoom in on a teeny tiny, infinitesimally small piece of the cable. They look at the slightly different forces pulling on each end of this tiny bit, and then, and this is the key, they apply Newton's most famous law, F equals ma, to connect that net force to how the little piece moves up and down.
And after you churn through all the calculus, this is what you get: the one-dimensional wave equation. Now, I know it looks a little intimidating, but just think of it like the cable's DNA. It's the universal rule book. It contains all the information about how any wave is allowed to travel along that cable.
And see that little letter C in there? That's not just some abstract number. It stands for a real physical speed, the wave propagation velocity. And the formula for it just makes so much sense. It only depends on the cable's tension and its mass. You crank up the tension, the wave gets faster. You make the cable heavier, the wave gets slower. Simple as that.
Okay, this is where all that theory gets really exciting, because now we can stop talking about abstract ideas and use this equation to calculate a real number for a real thing.
And for this, we're going to use the actual tech specs for a real deal heavy-duty steel cable. You know, the kind of thing you'd find on a ski lift or a cable car. We've got its size, its weight, its braking strength. Everything we need is right here.
So the source material walks us through the whole calculation. It uses the typical density of steel, its minimum braking stress, and then it applies a safety factor to figure out a realistic, everyday tension.
And when you take all those numbers from the datasheet and plug them into our little equation, you get this. The speed that a wave travels down this solid steel cable is about 200 meters per second. That's over 700 kilometers an hour, or around 450 miles per hour.
I mean, just let that sink in for a second. If you took a 50-meter-long cable and hit one end with a hammer, that vibration, that wave, would get to the other end almost instantly, in just a quarter of a second. That's a direct physical result of the math we just looked at.
But right, our cable isn't infinitely long. In the real world, it's bolted down at both ends, anchored to something solid. And this simple physical fact introduces one last really beautiful piece of physics into the puzzle. So you've got this wave just screaming down the cable at 200 meters a second. It's going to hit that solid anchor point really, really fast. What happens then? It can't just disappear, right? It reflects. The energy literally bounces off that fixed end and starts traveling back the other way.
Physicists call the first wave a progressive wave and the reflection a regressive wave. So now you've got two waves moving through each other on the very same cable.
And when these two waves, the original and its reflection, meet, they start to interact. It's a process called superposition. At some moments, the high point of one wave meets the low point of the other, and poof, they perfectly cancel each other out. For a split second, the cable goes completely flat.
But then, at other moments, the high point of the first wave lines up perfectly with the high point of the second one. When that happens, they add together. They reinforce each other and create these spots of huge vibration, way bigger than either wave was by itself. This constant cycle of canceling and reinforcing creates this incredible illusion, a wave pattern that doesn't even look like it's traveling. It just looks like it's vibrating in place, with some spots that don't move at all and other spots that move like crazy. This is what we call a standing wave. And here's the really mind-blowing part. For this stable pattern to even exist, the length of the cable has to be a perfect multiple of the wave's half wavelength. That means only very specific frequencies, or harmonics, are even allowed to exist on that string. This is the fundamental reason a guitar string plays a clear musical note, instead of just a bunch of random noise. So isn't that incredible? A single, elegant equation takes us all the way from an impossibly perfect idea to the messy, vibrating reality all around us. The next time you see a bridge cable, or a power line, or even a guitar, just remember you're not just looking at steel or string, you're looking at a physical solution to the wave equation, with these hidden waves constantly reflecting and interfering, creating a beautiful, stable, and predictable order out of chaos.